we're going to be talking about left hand and right hand rule today. ठीक है sir? I wanted to show a demonstration of it, but I actually can I? Hey, I can show left hand
You
and
have
right
a lot
hand
of
rule.
hands here, so.
No man, haha, very funny. Can someone neodymium magnets again? My favorite. Can someone give me a 9-volt battery and a piece of wire?
Yeah.
Yes, 9-volt battery. That was fast.
Yeah.
Oh wow, that was fast. Okay.
Who's the best employee in the world?
Employee in the world. So we are this new the world. Like not in even in the room, in the world. যত সব।
I have big ambitions.
Uh-huh.
Very big ambitions.
Yes.
I want to fly, but this does not fly.
Okay, so guys, we're gonna try something. I don't know হবে নাকি না. Hey, the flat plastic. There we go.
Best employee in the world.
Yes, that's Tezib, if you wanna know. Tezib likes to
Flex all the time.
blow his own trumpet.
চল আমরা
Okay, don't move.
গ্রিন রুম থেকে মনিটর করি চলো
আচ্ছা কোনো force, do you guys think there's gonna be any force?
নো
Okay.
অনেক বড় একটা কারেন্ট যাবে তোমার ব্যাটারিটা 5 মিনিটের মধ্যে শেষ
Oh wow, look, it's moving. Oh, amazing.
এটা ফেক
এটা actually দেখানোর জন্য you need a top end balance. Oh shit.
টপ 10 ব্যালেন্স লাগবে
হচ্ছে।
তুমি পারছো তো এটা ফেক
Watch this, watch this, watch this. এই যে কেবলটা আছে না?
No, it's actually moving.
দেখতেছো?
But explain the physics.
Hey guys, are you seeing this? This is crazy.
Yeah, I don't think they have noticed.
Hey, software engineer. Look at him. He's like, oh wait, I'll have to make a program about this one. So this I haven't seen this in my McGill days. খুব trigger হচ্ছে এখন নাকি? But এই যে দেখো, guys, watch this. Anyway, guys, it's just me now. But anyway, what I was showing you is Fleming's left-hand rule. So basically, let's try doing this and explaining it at the right time, at the same time. Sorry. So what basically happens is, let's look at this battery. So it has a positive terminal here, and it has a negative terminal here, positive terminal here. So when I connect it like this, because this is the positive terminal, current is flowing in this direction. So I'll just put a pen here to make it easy to remember that current's going to be flowing in this direction, all right? Or actually, let's put a screwdriver. That's more easy to understand. So what this screwdriver shows is current is flowing in this direction. And how am I saying that? Because look at this. This is a positive. This is a negative. Current flows from positive to negative. So basically, this is what I'm putting here. And guys, I'm not making this stuff up, right? I'll just put this here so that you can trust it a little more. And then what you do is I'll just hold this like this, right? So here we go. Current flow is going to be in this direction, downwards in this case. I'm holding it here and touch, release, touch, release. I'm trying to make them as small as possible, like my motions of the hand, so it doesn't look like as if I'm doing this because it's because of my hands. Okay, I'll try this again here. Touch. See, it moves. It moves in this direction. So we end up getting a force in this direction. At least that's what it looks like, right? This is the direction of the force. And I wrote F here. And the current flow was in this direction. No, it's actually not this way. It's actually downwards. My bad. So the current flow is downwards, I. And the force, actually what's happening is the wire is being pulled down. So as it's being pulled down, it looks like it's moving in this direction. But actually, let's do that again just to make it clear. Bring it between the two. Pull down, pull down, pull down. And if I was to reverse the entire battery and the magnet and everything, and do it again, up, up, up. See, you see that? Up, it moves up. I know it doesn't look so convincing, but trust me, it's happening. So basically, we have current flow in this direction, and we have a thing in this direction, right? So this is where we use the left-hand rule. And how do you use it? Force, field, current, right? Motion, field, current. A lot of people have different mnemonics to remember it by: motion, field, current, or mother, father, child, right? These are the usual ones, or Manchester Football Club, right? So yes, there's nothing other than these. এগুলোর বাইরে কোনো memory রাখার কোনো কিছু নাই. Right? So the one that I use is force field current. I know it's so cool, Marin, isn't it? It's like crazy. I haven't done this myself before, and like I'm actually pretty impressed with myself that I've been able to do it, thanks to like Tezzy being able to give me everything. But yeah, it's pretty damn cool. That's very true. And these magnets are really powerful. Look at that. Look at that. Did you see that? I put it here, and it comes. Oh my god, that's like crazy powerful. Anyway, I'll just put this here. I'm so hungry. So basically what happens is, oh my god, this is a mess. So we have, as I was just showing a few moments ago, so let's just keep the magnets here so it's easier to work with, or like, easier to explain. So we had two magnets like this. Don't, stay there. Stay. All right, great. So force field current. So, oh man. Diamond magnets can sometimes be a pain. Stay right here. Okay, so force field current. So force, field, and current. So the force we saw was basically upwards, right? Because the wire moved up. So if we have force, this is field. So we need to find out the direction of the field. The current was downwards. So if it's like this, that basically means this is a North Pole and this is a South Pole. I can't really prove this until I don't have a compass. I'll try to get a compass and try to show it to you guys. Basically, the point that I wanted to make was force, field, current, right? So always remember how to use the left-hand rule is if we try to apply it in the scenario that we just saw. We saw that first the wire was being pulled down like this, right? We saw the wire doing something. Oops, sorry. Oh, just forget it. So basically it was like this. So let's just draw the poles of the magnet. So this was one pole, this was another pole. We don't know the poles yet, but what we did see is that the wire experiences a force downwards. When the wire is here, it bent like this, right? It bent like this. So because it bent like this, this was being bent because it was being pulled in between the two, right? So downwards, it was pulled in. It was pulled in like that. So it moves down like this. So what does that mean? You have a force which is acting downwards, and you have a field between the two magnets, and the current is basically traveling along this direction. Oh my god, gone. So if we use the left hand rule to figure this out, the force, the field, and the current. So the force is going to be acting downwards. Field, we don't know, right? And it's going to be basically like this. So I know it looks really force field. It's hard to show underneath the magnet, interestingly. I never. Okay, so yeah, underneath the camera. Sorry. So basically, force is downwards. Field is from this side to this, and current is downwards, like downwards as in this direction. There's a trick, by the way, for those of you who have difficulty using left-hand rule. There's this American method. It's the left-hand rule, but they do it with the right hand. Get it? The right hand. So that's why it's American. So what they do is the palm represents force, and wait, let me check. Force, yes, it's like this. So the palm represents force. The fingers represent the field, and the thumb represents the current. It's basically the left-hand rule, but you're doing it with your right palm. So we can try it here also. I don't recommend this method. I'm just mentioning it for those of you who have difficulty moving your hand around, or if you don't have your left hand, for those who are handicapped, it can work also. Yes, I just said that. So force field current. So force field current with your left hand, and you can use your right hand to do it. So where the palm is the force, so that would be downwards, right? And the current was this way. As your thumb shows, current was down. So the field lines were in this direction. So field lines, as we always know, travels from north to south, right? Travels from north to south. So this is basically what happens. And so if I was to draw the magnetic flux lines in between the two, what would they look like? Right, there we go. That's why we experience the force like this. So, moving on, this is the basic concept of what's actually happening here. So we use the left-hand rule to do it. So you can use the left-hand rule, or we can use the right-hand grip rule. They're both equivalently applicable in this case. All right, so that's that. So basically, this is the left-hand rule. Notice, where did I use it? I used it in a scenario where you have an existing current flow made by this battery through this wire, and then what we did is we put the wire in a magnetic field, right? So this is the only scenario where you use the left-hand rule. I'm saying these points again so that you can remember. I hate these magnets now. So the points are, when you place a current carrying conductor in a magnetic field, which results in a force on the wire. And that's exactly what happened. The moment we connected it to the circuit, we saw that the wire moves, which was a resultant force. So basically, that's when you use the left-hand rule. When you place a current carrying conductor in a magnetic field and it results in the force, this is when you use the left-hand rule. So let me tell you one of the most common mistakes that students do with the left-hand rule. One of the most common mistakes that students do is, say, for example, this scenario. So we have north-south and the wire moves downwards, current is in this direction. So what they do is force field current, there's blue tack all over my fingers, force field current. So basically say they fix the current, right? And then when they try to fix the force, so the field, they're supposed to do this, right? So that it stays like that. But sometimes what they do is they do this. So the common mistake is basically, or say the force is supposed to be downwards, they do this, and then when they need to fix the current, they end up fixing the current but rearranging the direction of the force. It's a very, very common mistake that students do. So how do you work through this? How do you solve this? The ultimate answer to this is there's this practice that you can do, which helps a lot, which is basically once you identify one of the directions, for example, force field current, we know the force is downwards. What you can do is you can get a hold of it and not let it move, and then just move the other two. I know it's not really good to show, you can't clearly show it here like this. So let's just say this is field, and say for a specific scenario, let's say for this scenario, if we flip it around, I'm trying to flip it around. If we flip it around, then this is the north pole, right? So you can say force field is from north to south. So if it was like this, then what you should do is use your right hand to grip the field finger, right? Once you grip the field finger, then basically force and current, you can flip them around now. I know it's a kind of a silly thing to do, but it's actually a good way to exercise and practice the method of doing it. Yes, hold the finger, that's right. So you hold the finger, right? So force field current. So we know that the field is in this direction from north to south. Once we lock on that, we don't, this is a practice for beginners basically. We don't let it move around by basically having a grip on it, right? So like, you don't let it move away. And then what you do is you rotate the rest of your hand to figure out which direction what is going to be in, right? So it might be like this, might be like this, might be like this. So it basically helps in maintaining that specific direction. That's actually very useful. I find it useful for students who face difficulty because they do this, like, force field current. Say I say that the field is in this direction, okay, fine, from north to south, and then I say the current is in this direction. Like, oh, okay, current in this direction, I'll just flip it like this. Oh, that worked actually. So like, oh, wait, let me flip it like this. And they end up flipping the current and the force both together, the field both together, and end up getting the incorrect answer. So the best way to avoid that is basically gripping on one finger once you have the direction fixed, and then rearrange the rest of the hand. So that's basically the left hand rule. All right, so where do you use the right hand rule? When you basically have the situation that I was trying to show, is basically when you have a current carrying conductor placed in a magnetic field, and it cuts through the flux lines. Basically when I show this, is basically cutting through the flux lines. So as it cuts through the flux lines, what does this mean? It's inducing an EMF in it. So it's not going to show up here because we don't have enough turns here. To show a decent amount of flux linkage change or whatever, you actually have to have a powerful magnet and a number of turns. So that would basically be what we showed last class, which was basically instead of having just one piece of wire, we had a coil, right? And what did we do with the coil? I'm just doing this again because I really like showing it. It's fun physics. Like, I find it cool. Like, I know you guys might find it boring and everything, but like, just imagine that you can actually show these laws and rules as real physics happening in front of you. I feel an excitement in it, to be honest. So yes, what did we show last class? That we have this. If you move this, you get a deflection, right? Simple as that. So the reason this is showing a good deflection and the single wire didn't is because there's a lot of turns in this, and the more number of turns you have, the greater the flux lines cut. So yeah, very sad, Nafir. Actually, very sad. I wasn't able to show that. Maybe next time with a stronger magnet and maybe more number of turns. But fundamentally, this is what I would be showing, that like, this is what you get. So where do you use the right hand rule? So fundamentally, use the right hand rule when you have a conductor, current carrying conductor, placed in a change in flux linkage, or placed in a magnetic field such that it cuts through the flux lines and it induces an EMF. So yes, that's when you use the right hand rule. Again, for the right hand rule, force field current. You can't use the right hand rule in the scenario of the left hand rule because they will give opposite results. So this is the right hand rule, this is the left hand rule. Again, when do you use the right hand rule? When you have a current carrying conductor placed you have a current carrying conductor placed in a magnetic field which results in a force. This is when you use the left hand rule. When do you use the right hand rule? When you take a conductor, right? You take a conductor, you place it in a magnetic field, and you make it move, right? That's basically the force in the magnetic field, having a field blah, and it induces an EMF in a specific direction. This is when you use the right hand rule. You'll see in your exam hall that there's going to be most students are naturally right-handed, right? Majority of people are right-handed. So even if we say left hand, they end up using the right hand, especially when they're not thinking about it. So when you're in your exam hall and if you haven't practiced enough, or if you see someone who hasn't practiced enough, you're going to see lots of students suddenly doing the left hand rule all over the place. And then there's going to be this one guy using his right hand to find the answer, right? So basically this is how you use the right hand and the left hand rules. So it's very simple. It's very straightforward. I'm going to say it again because this is the most important part. Left hand rule used when you have already a current in a magnetic field and it induces a force or creates a force. So when a current carrying conductor is placed in a magnetic field and results in a force, you use the left hand rule. Where do you use the right hand rule? When a conductor is placed in a magnetic field, and moved in such a way that it cuts the flux lines and results in an induced EMF. So that's basically the answer. So this is the basic way of doing the left hand, the right hand rules. It's very easy, very straightforward, doable, and there aren't any problems in solving that. I hope you guys got that. If you have any questions, please feel free to ask, and we'll get going right after you're done.